this lecture is due to extremal Peisert-type graphs without strict EKR properties. So
thank you very much for the introduction, and let me start. So first of all, let us observe what has been discussed so far. In lecture 1, we discussed a proof that Paley graphs of square order have the strict EKR property. In lecture 2, we discussed EKR properties of graphs. In particular, we started a discussion on EKR properties of Peisert-type graphs, which are a class of graphs generalizing Paley graphs of square order. And in lecture 3, we focused on possible analogs of Hilton-Milner theorem for Paley graphs of square order and a subclass of Peisert graphs. Let us recall what are the main questions for graphs in flavor of EKR type results. First, if we have a family of graphs, is it possible to define the notion of intersecting for vertices, define canonical cliques, and show that they are maximum? Second, if the answer for question 1 is positive, is it possible to decide whether the canonical cliques are the only maximum cliques? If there are non-canonical cliques, can we enumerate them and describe their structure? Third, if the answer for question 2 is positive, that is, the maximum cliques are known, is it possible to decide whether there exist maximal cliques that are not maximum? If there are any, can we enumerate second largest maximal cliques and describe their structure? Let us recall the basic definitions of a Cayley graph and a Peisert-type graph. Given an abelian group G and a connection set S, which is a identity-free subset of G and inverse closed, the Cayley graph K of GS is an undirected graph whose vertices are the elements of G, such that two vertices G and H are adjacent if and only if their difference belongs to S. Let P be a prime and Q a power of P. Let FQ be a definite field with Q elements. FQ plus denotes its additive group, and FQ star denotes its multiplicative group. Let S be a union of M cosets of the multiplicative group of the subfield FQ star of the field FQ squared star, where M is between 1 and Q inclusive. That is, S can be written as a union of M cosets of such form. Then the Cayley graph over FQ squared plus over this additive group with connection set S is said to be a Peisert-type graph of type MQ. So the first parameter denotes the number of cosets involved in the connection set, and Q is a power of P, the second parameter. So this graph has, such graphs have Q squared vertices. In this lecture, we discussed many properties of Peisert-type graphs. Let us start with basic ones. The class of Paley graphs of square order is a special case of Peisert-type graphs. Second, every Peisert-type graph of type MQ can be naturally defined on the points of the affine plane HG to Q, with 2 points being adjacent whenever the line through these points belongs to one of M prescribed parallel classes of lines. The canonical cliques in a Peisert-type graph of type MQ are exactly the lines from M prescribed parallel classes defining the graph. Third, the affine plane HG to Q can be viewed as an orthogonal Q plus 1 times Q squared array OA of type OA Q plus 1 comma Q, and every Peisert-type graph of type MQ can be viewed as the block graph of an orthogonal array of type MQ obtained from this array OA q plus 1q by choosing the subset of m rows corresponding to m prescribed classes of parallel lines. It is well known, let us give some comments on the number of pairwise non-isomorphic Peisert-type graphs. It is well known that the stabilizer of the 0 point of the affine plane hg to q acts pre-transitively on the set of lines through this point, through the 0 point. This implies that for any prime power q, all Peisert-type graphs of type 3q are isomorphic. Since the complement of a Peisert-type graph of type mq is a Peisert-type graph of type q plus 1 minus mq, we conclude that the number of pairwise non-isomorphic Peisert-type graphs of type mq is equal to the number of pairwise non-isomorphic Peisert-type graphs of type q plus 1 minus mq. In particular, whenever q is less or equal to 5, that is 2, 3, 4, or 5, there exists a unique Peisert-type graph of type mq up to isomorphism for any admissible value of m. That is, m is between 1 and q inclusive. Previously, in a recent paper, we applied the known bound, some known bound on block graphs of orthogonal arrays to Peisert-type graphs, and thus show it the following condition, the following theorem, prove the following theorem, which is actually a corollary. If q is greater or equal to m minus 1 squared, then all Peisert-type graphs of type mq have the strict-EKR property. Moreover, when q is a square, there exists a Peisert-type graph of type square root of q plus 1 q without the strict-EKR property. Okay, so the first part of this theorem is a corollary of the result by Gotsil and Marr obtained in a general form for block graphs of orthogonal arrays. But the second result on the existence of a Peisert-type graph without the strict-EKR property and corresponding to the equality in this strict inequality. This was our result, which is not a corollary. We obtained it by hands, and however, we were not able to describe explicitly these graphs that correspond, these Peisert-type graphs that correspond to the equality in this inequality. Given a prime, somehow we will, so this family, actually, this lecture and the results that will be discussed today are devoted to this family of graphs. We will provide an explicit construction of this graph and characterize them. Given a prime power q, there exists the smallest value of m, say mq, such that there exists a Peisert-type graph without strict-EKR property, and we call such parameter mq extremal. In theorem 1, we show it that if q is a square, then mq is equal to square root of q plus 1. In general, the bound from theorem 1 says that mq is greater or equal to square root of q plus 1. A Peisert-type graph of type mqq, so mq is the smallest value of m, such that there exists a Peisert-type graph without strict-EKR property. A Peisert-type graph with exactly this parameter mq without strict-EKR property is called extremal. And it is important that it is extremal with respect to the property of not having a strict EKR property.
Yeah, I have a question.
Yeah, please.
So depending on the choice of the value m, you may or may not have strict EKR property. But you're interested in the smallest value m, such that.
So the theorem 1 says that if m is relatively small with respect to q, then we always have the strict EKR property.
Yeah.
But when
but then
grows,
there's a
if m grows,
there may not be.
Yeah, if m grows, there is the first case, the smallest m, such that there exists a Peisert-type graph without strict EKR property. This is the first case when the strict EKR property fails.
Yeah, but then if you add 1 to m, then can you say that there is a Peisert-type graph without EKR property? Is there a kind of threshold?
So the situation is as follows. We have a lattice of Peisert-type graphs with respect to inclusion. I mean,
of connection set.
Yeah, with respect to inclusion of connection set, better to say it's a quite complicated lattice. I mean, the idea is that if some Peisert-type graph fails to have the strict EKR property, then if we extend its connection set, if we add more cosets to the connection set, then the resulting graph also fails.
I see. Okay, thank you very much.
Okay, thank you for your question. Let me add one more comment. So if we add more cosets, we obtain a non-canonical clique, which is not a line. And if we add even more cosets, this non-canonical clique that is not a line will be a non-canonical clique in the resulting graph as well. Okay, let us consider several tables that provide the numbers of pairwise non-isomorphic Peisert-type graphs. If Q equals 4, we consider the cases when M equals 3 and 4, and we have one graph in each case. And we said that if Q is at most 5, then there is exactly one Peisert-type graph of for each M, and you can see that the second row's sharp graphs in each column contain 1, which means that there is exactly one graph. The row number 3, strict EKR, shows how many of the graphs in the second row do have strict EKR property. And the third, the row number 4, shows the number of Peisert-type graphs from the second row that do not have a strict EKR property, without strict EKR property. So if for each column, the number in the second row is the sum of the numbers in the third and in the fourth row. The case Q equals 7 is interesting because when M equals 4, just half of Q plus 1, we have, this is the first case when we have at least two pairwise non-isomorphic Peisert-type graphs with the same parameters of the same type, and both of have strict EKR property. And how can we compute the number MQ for in each table? So each table, we look at the row number 4 in each table and go from the left to the right. And the first appearance of one of non-zero, the first appearance of a positive number of graphs without strict EKR property shows the column and the parameter m, which is extremal. And according to these tables, we thus have m4 equals 3, m5 equals 4, m7 equals 5, and m8 equals 5. In these 4 cases, and we point out that in these 4 cases, an extremal graph is unique. Let us consider more tables. Q equals 9. You can see that we get more graphs in the middle. For m equals 4, 5, and 6, we have 2 graphs. And the first appearance of 1 in the row number 4 is in column corresponding to m equals 4. So we conclude that m9 is equal to 4. And in a similar way, we conclude that m11 is equal to 7. And you can see that for q equals 11 and m equals 6, we have already 4 pairwise non-isomorphic graphs. In these 2 cases, in these 2 more cases, an extremal graph is unique. We also made computations for q equals 13 and 16, and so my point is that these tables grow, and for example, if q equals 16, the behavior, the general behavior of such a table is as follows. When m is relatively small, then the row number 4 is empty. Then we meet the first positive value in some column, and this is the extremal value of m. Then we see several columns such that both graphs with strict EKR property and without strict EKR property exist, and then from some m, in the case of q equals 16, from m equals 10, we have only graphs without strict EKR property. And if we have such a situation that for some value of m, all the graphs are without strict EKR property, then we can conclude that for all m that are greater than this value, all the Peisert-type graphs are also without strict EKR property because of their inclusion. This is the table for q equals 17 and m16 equals 10, and an extremal graph is unique. Q equals 19 is the last complete table from this list of tables. All the entries are computed, and m19 is equal to 11, and an extremal graph is unique. In the next case, you can see that the number in the middle cases, the number of pairwise non-isomorphic graphs is already more than 200, and m23 is equal to 13, and an extremal graph is unique, but we were not able to compute these values. Maybe we will be able to compute m equals 16 and 17. but it gets harder to enumerate all the cliques when the number of cosets grows. And the last table, which is also incomplete, is the case Q equals 25, and you can see that it is it can be seen from this table that m, the parameter, the extremal parameter m25 is equal to 6, but we even don't know the number of graphs for m equals 10, 11, 12, and 13. I hope it can be done, and my program is computing right now. Yeah, but so far the idea, I think the idea and the definition is clear. And in all the cases, for all prime powers Q, at most 25, an extremal graph is unique. This lecture is mainly devoted to the following problem: determine all extremal Peisert-type graphs without strict-EKR property. And let us immediately present our main results, which were published on arXiv just several days ago. Theorem, the first theorem, we will have three theorems, three main results. The first reads as follows: let Q equals p to the power of n, where p is a prime and n is a positive integer. Let X be an extremal Peisert-type graph defined on FQ squared. If n equals 1, that is Q is prime, and p is greater or equal to 3, then X is of type p plus 3 over 2p, and X is unique up to isomorphism. If n is greater than 1, then X is of type p to the power of n minus k plus 1, comma q, where q is the largest proper divisor of n. Note that the result in case n equals 1 follows from some known results from the theory of directions in affine planes, and the case n is strictly greater than 1 was newly developed. Theorem 3. Let Q be the square of a prime power. So Q is a prime power and a square. There are exactly Q plus 1 times square root of Q extremal Peisert-type graphs defined over FQ squared, and each Peisert-type graph of type 3Q is a subgraph of exactly one such extremal graph. Moreover, if X is such an extremal graph, then the following statements hold. X is unique up to isomorphism. In fact, X is isomorphic to the affine polar graph VO plus for square root of Q. X has exactly square root of Q plus 1 canonical cliques containing 0 and the same number of non-canonical cliques containing 0. Moreover, these 2 times square root of Q plus 1 cliques lie in the same orbit under the action of the automorphism group of X. There is no, the next statement, there is no Hilton-Milner type result. All maximal cliques in X are maximum cliques, and the weight distribution bound is tight for both non-principal eigenvalues of X. And the third main result is devoted to the case when Q is a cube but not a square. Let Q equals R to the power of 3, where R is a prime power and a non-square. There are exactly R plus R times this sum, R to the 5 plus R to the 4 plus R to the 3 plus R squared plus R plus 1 extremal Peisert-type graphs defined over FQ squared, possibly isomorphic. Moreover, if X is such an extremal graph, then the following statements hold. X is unique up to isomorphism. And second, maximum cliques in X can be explicitly determined. In particular, X has exactly R squared plus 1 canonical cliques containing 0, and R squared plus R plus 1 non-canonical cliques containing 0. And
can I ask a question on this theorem? You
yes,
say
please.
that there are some certain number of extremal graphs. Is it the up to isomorphism, or you're just counting the number of connection sets?
The number of connection sets.
I see.
Up to isomorphism. Isomorphism, yeah. It is unique. All of them are isomorphic.
I see. Thank you.
And main result number 4, which is not a theorem but a remark, which is quite important. Let Q be the smallest prime power, which is not neither a prime nor a square nor a cube. That is the 5th power. Q equals 2 to the 5. Let epsilon be a primitive element in FQ such that epsilon is a root of the irreducible polynomial t to the 5 plus t squared plus 1, and let beta be a root of the irreducible polynomial t squared plus t plus 1 over the binary field. Note that beta belongs to the difference f squared minus fq. Consider the Peisert-type graph x1 induced by the f2 subspace f1 generated by the elements. So we consider this elements as elements of the finite field f2 to the 10. The square root of this number is 32, so we need the sharp cliques in these graphs, in these Peisert-type graphs, have size 32, and it suffices to pick up 5 vectors, 5 elements, 5 generators of a subspace. Then we consider all the differences that occur in this subset, in this subspace, and we say that x1 is induced by this subspace this means that we consider the corresponding Peisert-type graph corresponding to all the differences in this subspace. So if some difference occurs in the subspace, we add the corresponding coset to the connection set.
So you mean V1, X1 is defined by V1, just V, not V.
Yeah, by V1, sorry.
Yeah.
Similarly, consider the Peisert-type graph X2 induced by F2 subspace V2 generated by the elements 1 epsilon, epsilon squared, epsilon cubed, and beta. And it can be verified by hands or a simple computer program that Vi is a non-canonical clique in Xi, and each Xi, where I is 1 or 2, is a Peisert-type graph of type 1732. This, according to the bound, we have these graphs extremal, and we have verified that X1 is not isomorphic to X2, showing that there are at least 2 non-isomorphic extremal Peisert-type graphs defined over the field F2 to the to the 10. So we conclude that the uniqueness result we met in the tables and we met in the prime, in the square, and in the cubic case, this uniqueness result does not extend to all prime powers q. Let us recall and maybe even introduce a recent result by Asgharli and Ip on the structure, on the algebraic structure of the L-star cliques in certain Peisert-type graphs. Let X be a Peisert-type graph of type MQ, where Q is a power of an odd prime P, and M is at most half of Q plus 1 over 2, or at most half of Q plus 1. Q plus 1 is the total number of cosets, and if at most half of the cosets is involved in the connection set, then any maximum clique in X, in an arbitrary Peisert-type graph, any maximum clique containing 0 is an FP subspace of FQ squared. So if M is at most half of the total number of, it is important that P is an odd prime, and it is important that if M is at most half of the total number of cosets, then all maximum cliques, both canonical and non-canonical, have nice algebraic FP subspace structure. Further, for any prime power Q that is not a prime, we introduce an explicit infinite family of extremal Peisert-type graphs of type MQQ without strict EKR property and discuss its properties. Let Q be equal R to the power of N, where R is a prime power and N is prime. Assume that the finite field FQ squared is written as the set of sums X plus Y beta, where X and Y run over FQ, and B is the root of an irreducible polynomial over FQ, considering FR to the power of N as an n-dimensional FR vector space, underline the affine space HG of NR, let H be an additive coset of n-1 dimensional subspace or in FR to the power of N. Equivalently, let H be a hyperplane in HG of NR. Note that the size of H is R to the power of n-1. In other words, okay, I think it should be clear. And then let us define a connection set S of a Peisert-type graph based on H. S of H is denoted to be the union of the following cosets. First, we take the coset FQ star, which is the subgroup, and all the cosets with representatives H plus beta, where H runs over capital H. So we say that this okay, let YQN of H be the Peisert-type graph of type R to the power of n-1 plus 1, there are so many cosets in this definition. Let YQN of H be the Peisert-type graph defined by the generating set S of H. And we proved the following theorem, the following proposition, the following statement, that for any two hyperplanes H1 and H2 in HG of NR, the graphs YQN parameterized by H1 and H2 respectively are isomorphic. And we may write YQN instead of YQN of H. Given a prime power Q, the question is how many graphs YQN have we defined? Let Q be equal to P to the power of M, where P is prime and M is an integer, where M is greater or equal to 2. Let D be the number of different prime divisors of M. We have defined exactly D graphs of YQN. Indeed, let Kn, K1, so on, Kd be the divisors of M, such that M over K1, so on, M over Kd are different primes arranged as an increasing sequence. Put an I to be equal to M over Ki and Ri to be equal to P to the power of Ki. Then for any I from the set from 1 to D, we have Q equals Ri to the power of Ni. So we can represent Q as a prime power to the power of a prime. And we have thus defined exactly D graphs, YQN1, so on, YQ and D. Let us continue discussion on these graphs. Let Q be equal to R to the power of N, where R is a prime power and N is a prime. Consider the graph YQN. The following statements hold. The graph YQN is a Peisert-type graph of type R to the power of N minus 1 plus 1, R to the power of N, and the graph YQN fails to have the strict-EKR property. We conjecture that given a prime n, the graph YQN has exactly R to the power of N minus 1 over R minus 1 non-canonical cliques containing 0. And this conjecture was shown to be true when N is 2 or 3. Let us give a classification of extremal Peisert-type graphs without strict-EKR property. Our main result was that we know the uniqueness of this graph, or of the uniqueness of an extremal graph when Q is a square or a cube that is not a square. And let us introduce a more detailed classification. Let Q be equal to P to the power of M, where P is prime and M is an integer greater or equal to 2. Let K1, so on, Kd be the divisors of M, such that M over K1, so on, M over Kd are different primes. Order it, consider it as an increasing sequence. Let N1 be equal to M over K1 and R1 be equal to P to the power of K1. So we consider the smallest prime number from this sequence. Then the following statements hold. First, the graph YQN1 is an extremal Peisert-type graph without strict-EKR property. And second, if N1 is is 2 or 3, then YQN1 is the only up to isomorphism extremal Peisert-type graph without strict EKR property. As we already said, if Q equals 2 to the 5, then there exists at least 2 non-isomorphic extremal graphs without strict EKR property, Y 32, 5, and 1 more. And let us formulate the first problem in this lecture. If Q equals R1 to the power of N1, where R1 and N1 are as above, N1 is the smallest. So R1 to the power of N1 is a representation of Q such that N1 is the smallest prime. And suppose that N1 is greater or equal to 5. The question is how many pairwise non-isomorphic extremal Peisert-type graphs of type MQQ without strict EKR property does there exist? Let us focus on the case of when Q is a square, Q is equal to R squared. Note that in this case, the subfield FR is a hyperplane, a line in the affine space in the affine plane HG to R. Consider the extremal Peisert-type graph YQ2 of FR of type R+1 Q. We have put H equals FR in the definition. We have chosen H to be the subfield FR, which is a line and a hyperplane. Let Q be the set of all elements of the field FQ star, or of the multiplicative group FQ star, such that all elements gamma from FQ star such that gamma to the power of R+1 equals 1. So this object can be viewed from different points of view. First of all, this is a subgroup. This is the subgroup of order R+1 in FQ star. Second, this is the kernel of the norm mapping norm mapping from FQ star to FR star, and so this this set was already considered in lecture 3 in one of the constructions of maximal one of the constructions of maximal cliques in Paley graphs of square order, and here we have one more appearance of this object. Let S we denote a connection set S in terms of Q as follows. We consider the union of all cosets whose representatives are elements delta plus beta, where delta runs over Q. And let XQ be the Peisert-type graph of type R+1 Q defined by the generating set S. So what is known already? We know that YQ2 of FR is an extremal graph and it is unique. And if we define another Peisert-type graph of the same type R+1 Q, then it turns out that the graphs YQ2 of FR and XQ are isomorphic. And the isomorphism is established by by connecting two generating sets, namely the generating set S of FR can be obtained from S by multiplication from the left by any non-degenerate matrix sigma sigma to the power of R 1 1, where the elements in the first row are different. So we know from now we know that XQ is just one of the another form of.
What do you mean by multiplying the matrix? Sorry,
Okay,
in
so
the previous slide.
the idea, and let me explain the idea. The group GL of 2R acts on the set of
acts on the affine plane.
On the affine plane, and if so, since the set of generators is the pencil of lines through zero without a pencil of lines through zero without zero, if two such pencils are equivalent under the action of GL of 2R, if they are obtained from each other by multiplication of this matrix, then we can conclude that the graphs are isomorphic.
Okay, thank you.
The details can be found in the preprint, but it turns out that we can choose any sigma. So, and this special matrix. Let us describe a non-canonical clique in XQ in some algebraic form. So we know from the result that by Asgarli and Ip that each non-canonical clique on zero, containing zero, must be a subspace. And now in our case, it's a two-dimensional subspace over f square root of q, and we consider the following two-dimensional subspace generated by the vectors 1 plus beta and epsilon to the power square root of q plus epsilon beta. After some not so difficult steps, we conclude that CQ has okay, let us go step by step. So first of all, we replace f square root of q by a and b. The a and b run over f square root of q independently. Then we rearrange the terms and get a plus b epsilon square to the power square root of q plus a plus b epsilon multiplied by beta. Then we can, using the property of the field automorphism, we can substitute a plus b epsilon to the square to the power square root of q, and we can change it to a plus b epsilon, and altogether to the power of square root of q. And the second term is the same, a plus b epsilon times beta. Then, if a and since epsilon is a primitive element, in particular, 1 and epsilon are linearly independent over this subfield, and if a and b run over f square root of q independently, then the element a plus b epsilon run over fq. So we replace a plus b epsilon by gamma and get this form. Actually, this is the conjugation, the analog of the conjugation. And if we factor out 1 gamma, then we see that this element belongs to the connection set of xq. So so if gamma is not zero, if gamma is non-zero, then this element belongs to the connection set of xq, because element gamma to the power of square root of q minus 1 belongs to the subgroup of order square root of q plus 1. So in other words, we described a subspace in the connection set. And the following statements about this subspace hold. The subspace CQ induces a non-canonical clique in XQ. Moreover, the intersection of any canonical clique in XQ containing 0 and CQ has exactly square root of q minus 1 non-zero elements. These elements are given by the elements gamma from FQ star lying in the same coset of F square root of Q star in FQ star. Second, for any I from the set 0, 1, so 1 square root of Q, the set epsilon to the power of I, where epsilon is the primitive element, CQ multiplied by epsilon to the power of I induces a non-canonical clique in XQ. And for any I and j from the same set, such that I is not equal to j, we have that the intersection of such non-canonical cliques is trivial. It's just the 0 element. And third, the square root of plus 1 non-canonical cliques, CQ epsilon CQ epsilon squared CQ so on epsilon to the power of square root of Q CQ are the only non-canonical cliques in XQ containing 0. So in other words, we have described the graph YQ2 in an alternative way in terms of a graph XQ that which has different nature, and we have described the non-canonical, all the non-canonical cliques containing 0 in some nice algebraic way in terms of primitive elements, field automorphisms, and so on. Let me recall the definition. It was claimed in the first main result, in one of the main results, that in the square case, the extremal graph is isomorphic to an affine polar graph. And let me recall some basic facts about affine polar graphs. Let V be a 2E dimensional vector space over a finite field FQ, where E is greater or equal to 2 and Q is a prime power, provided with the hyperbolic quadratic form HQ of X equals X1, X2 plus X3, X4, so on, X2E minus 1, X2E. The set HQ plus of zeros of HQ is called the hyperbolic quadric, where E is the maximal dimension of a subspace in Q plus. A generator of HQ plus is a subspace of maximal dimension in HQ plus known to be equal to E. This maximal dimension is equal to E, the half of the dimension of the underlying vector space. Denote by VO plus 2EQ the graph on V with two vectors X and Y being adjacent if and only if the value of the form HQ on the difference of X and Y is equal to 0. This is a Kelly graph. And this graph is known as an affine polar graph of hyperbolic type. This graph is known to be vertex transitive stronger regular graph with the parameters given on the slide. We actually don't need the detailed description of these parameters. But one of our results in this project is as follows. Let V of NR be an n-dimensional vector space over the finite field Fr, where n is greater or equal to 2 and r is a prime power, let f of x1, x2, so on xn be a quadratic form on V of nr. Define a graph GF on the set of vectors of V of nr as follows: for any u and v from V of nr, u and v are adjacent if and only if the value of the form on the difference of these vectors is equal to 0. Two quadratic forms f1 and f2 are said to be equivalent if there exists an invertible matrix B from the group GL of nr such that f1 of bx is equal to f2 of y. It can be shown that the linear change of variables gives an isomorphism of two graphs associated with quadratic forms, and thus the following lemma holds. Let f1 and f2 be two equivalent quadratic forms, then the graphs gf1 and gf2 are isomorphic. And as a corollary, so we know the representation of the affine polar graph VO plus of 4 square root of q in terms of the hyperbolic quadratic form, and using some algebraic properties of the set q, we were able to describe xq as a graph associated with some quadratic form over the corresponding finite field of order square root of q. And then we just found that these quadratic forms are equivalent by establishing a linear change of variables for them. And thus we conclude that xq is isomorphic to VO plus of 4 square root of q. So thus we have two isomorphisms. The extremal graph y q2 is isomorphic to xq, which is isomorphic to the affine polar graph VO plus 4 square root of q. And thus we conclude that y2q is also isomorphic to VO plus of 4 square root of q. Let us recall some well-known facts about affine polar graphs of hyperbolic type. The following statements hold. There is a one-to-one correspondence between generators of the quadratic HQ plus and maximal cliques in in the affine polar graph VO plus 2E are containing the vector 0. Second, the graph VO plus of 4R has exactly 2 times R plus 1 maximal cliques containing 0 vector, and these are the generators. 3, all maximal cliques of an affine polar graph VO plus of 2ER are equivalent under the action of the automorphism group. And the fact number 4, an affine polar graph VO plus 2ER is a rank 3 graph. That is, it is arc-transitive and its complement is arc-transitive. Thus, some of the properties of the extremal graph XQ, as well as its isomorphic graph, as well as the isomorphic graph YU2, some of their properties are implications of known results on affine polar graphs. In particular, the fact that we have no Hilton-Milner type result in the square case is the implication of the fact that all maximal cliques in affine polar graphs are maximum. The following lemma gives a lower bound for the number of non-zeros, that is the cardinality of the support for an eigenfunction of a stronger regular graph, known as the weight distribution bound. It is a special case of a more general result for distance regular graphs. We already discussed it in our lecture 3. But let us recall and in the case of stronger regular graphs and provide more details. Let X be a primitive stronger regular graph with non-principal eigenvalues θ1 and θ2, such that θ2 is negative and θ1 is positive. Then an eigenfunction of X corresponding to the eigenvalue θ1 has at least 2 times θ1 plus 1 non-zeros, and an eigenfunction corresponding to the eigenvalue θ2 has at least minus 2 θ2 non-zeros. And the following lemma gives a combinatorial interpretation of the tightness of the weight distribution bound in terms of special induced subgraphs. Let X be a primitive stronger regular graph with eigenvalues θ2 and θ1 as above. Then the following statements hold. This lemma has 4 items, and it is better to look at item 1 and 2 together and then look at items 3 and 4. Item 1, for a θ2 eigenfunction f, if the cardinality of support of f meets the weight distribution bound, then there exists an induced complete subgraph in X with parts T0 and T1 of size minus θ2. Moreover, up to multiplication by a constant, f has value 1 on the vertices of T0 and value minus 1 on the vertices of T1. And a similar result, it follows from the fact that the complement, taking the complement of a stronger regular graph preserves the eigenspaces but swaps them in some way. We thus get item 2. For a θ1 eigenfunction f, if the cardinality of support of f meets the weight distribution bound, then there exists an induced pair of isolated cliques T0 and T1 in X of size minus θ2 bar, which is equal to 1 plus θ2, 1 plus θ1. Moreover, up to multiplication by a constant, f has value 1 on the vertices of T0 and value minus 1 on the vertices of T1. So the idea is as follows. If the weight distribution bound is tight, then we have an induced subgraph of a special form. Either in case of stronger regular graphs, we have either complete bipartite subgraph with parts of size minus θ2, or a pair induced pair of isolated cliques of size 1 plus θ1. So if the weight distribution bound is tight for some non-principal eigenvalue of a stronger regular graph, then the eigenfunction necessarily has this form. And items 3 and 4 provide the converse statement. If X, but in some special case, if X, item 3, if X has Delsart cliques and each edge of X lies in a constant number of Delsart cliques, for example, X is an edge-transitive stronger regular graph with Delsart cliques, then any copy as an induced subgraph, any copy of the complete bipartite graph with parts of size minus θ2 in X, not into, but in X, gives rise to an eigenfunction of X whose cardinality of support meets the weight distribution bound. And the eigenfunction is of the form given in item 1. And item 4 is just the converse statement for the positive eigenvalue. If the complement of X has Delsart cliques and each edge of X lies in a constant number of Delsart cliques, for example, each edge of the, sorry, this is a typo, each edge of the complement of X lies in a constant number of the Lessard cliques. For example, X is a co-edge transitive strong irregular graph whose complement has the Lessard cliques. Then any copy as an induced subgraph of a pair of isolated cliques of size θ1 plus 1 gives rise to an eigenfunction of X whose cardinality of support meets the weight distribution bound and which is of the form given in item 2. So if the weight, in other words, for short, if the weight distribution bound is tight, then there exists as a certain induced subgraph. And if each edge lies in a constant number of the Lessard cliques in some in the graph itself, or each edge of the complement lies in the constant number of the Lessard cliques, then we have the corresponding converse that any embedding of the special subgraph gives rise to an eigenfunction whose cardinality of support meets the weight distribution bound. And this slide, the next two slides are devoted. Okay, so we can note that Peisert-type graphs, a Peisert-type graph has the Lessard cliques, and its complement does as well. And we know that XQ is isomorphic to an affine polar graph, which is a rank 3 graph. So we know that the converse is the converse of the statement on the weight, on the tightness of the weight distribution bound holds. So items 3 and 4 can be applied. Let us apply item 3. It says that it suffices to find a complete bipartite graph with an induced complete bipartite graph with parts of size minus θ2, and thus define an eigenfunction, define a function on this subgraph, one on one part, minus 1 on the other part, and 0 otherwise. And we can immediately conclude that this is an optimal eigenfunction, an eigenfunction whose cardinality of support meets the weight distribution bound. And the structure of this subgraph we found is as follows: let T0 equals Q and T1 equals Q beta. We again meet this special set Q. Note that T0 and T1 are subsets of lines with slopes 1 and beta in the affine plane HG to Q. These lines do not intersect with S and thus are co-cliques in XQ, which means that T0 and T1 are co-cliques, even not maximal co-cliques. These co-cliques T0 and T1 can be embedded in a larger co-cliques, the corresponding lines. They are subsets of lines not involved in the connection set. Let gamma 1. Okay, this is a proof that this is a complete bipartite graph. Actually, we don't need this proof. We can skip it because of the result. But it can even be verified by hands that their difference, gamma 2 beta minus gamma 1 of two arbitrary elements of different parts of this subgraph, belongs to S. Just one row statement. Thus T0 union T1 induces a complete bipartite subgraph in XQ with parts T0 and T1 of size square root of Q plus 1. And if we define a function of this form as was said above, then we conclude that this function is Okay, so, sorry, let us go back to the previous slide. We need to verify that this is a complete bipartite graph, and actually this row is needed. So we just consider this difference by hands and use the properties of the subgroup Q and conclude that this difference gamma 2 beta minus gamma 1 is equal to gamma 1 prime times gamma 2 prime plus beta, where gamma 1 and gamma 2 prime are uniquely determined elements from Q. This means that the difference belongs to the set S, to the generating set S of XQ. So XQ is somehow induced by Q, by the set Q. This means that T0 union T1 induces a complete bipartite subgraph in XQ with parts T0 and T1 of this size, and we don't need to verify in general to conclude that this is an eigenfunction. We need to verify that each vertex outside of this induced complete bipartite subgraph, each vertex has the same number of neighbors in the parts of this subgraph, and this number may depend on the choice of the vertex outside, but for each vertex, the numbers of neighbors in the parts is the same. Because of item 3 on the theorem on the tightness of the weight distribution bound, we don't need to verify that each vertex outside of this complete bipartite subgraph is good. So we just conclude that this is an eigenfunction, and its cardinality of support meets the weight distribution bound. Since XQ is isomorphic to an affine polar graph, we conclude that the weight distribution bound is tight for the negative non-principal eigenvalue of such affine polar graphs, and this is a contribution to a different project on affine polar graphs. So in the previous workshop organized by the Mathematical Center in Akademgorodok, Rhys Evans gave a talk and discussed the tightness of the weight distribution bound for stronger regular affine polar graphs and polar graphs, and he discussed the case of the positive non-principal eigenvalue. But we were able to prove this. To show a similar result for the negative non-principal eigenvalue in for some subfamily of affine polar graphs of hyperbolic type. And it is interesting that we did it in a uniform way. We don't need to consider any cases. Problem 2. Let us formulate the second problem in this lecture. Characterize minus square root of q minus 1 eigenfunctions of xq whose cardinality of support meets the weight distribution bound, which is 2 times square root of q plus 1. And let us go to the conclusion of this lecture and in this mini course. We need to recall what are orthogonal arrays and their block graphs. An orthogonal array OA of Mn is an m times n squared array with entries from an n element set W with the property that the columns of any 2 times n squared subarray, that is a pair of rows, the columns consist of all n squared possible pairs of elements. The block graph of an orthogonal array OM OA of Mn denoted by D with index OA of Mn is defined to be the graph whose vertices are columns of the orthogonal array, where 2 columns are adjacent if there exists a row in which they have the same entry. Let SRI be the set of columns of OA of MN that have the entry I in row R. These sets are cliques, and since each element of the n element set W occurs exactly n times in each row, the size of such cliques is n for all I and R. And we call in lecture 2 we called these cliques canonical in the block graph of the orthogonal array. We also know that a simple combinatorial argument, I mean, it's well known that the block graph of an orthogonal array is strongly regular. Recently, we explored the fact that each Peisert-type graph of type MQ can be realized as the block graph of an orthogonal array OA of MQ. Moreover, there is a one-to-one correspondence between canonical cliques in the block graph of orthogonal array and canonical cliques in a given Peisert-type graph. Originally, the definition of canonical cliques in Peisert-type graphs were given independently, but then we realized that these two definitions agree with each other. And in this project discussed in this lecture, in the recent preprint, we defined extremal Peisert-type graphs having non-canonical cliques. In fact, this definition can be naturally extended to the class of block graphs of orthogonal arrays obtained from affine planes different from HG to Q and having non-canonical cliques. It is well known that an orthogonal array OA of Mn is equivalent to m-2 mutually orthogonal Latin squares. Further, it is well known that no more than n-1 mutually orthogonal Latin squares of order n exist. This implies that for an orthogonal array OA of Mn, we necessarily have m is less or equal to n+1 and a set of n-1 mutually orthogonal Latin squares, or as an orthogonal array equivalently, an orthogonal array OA n+1n is called complete. It is well known that the existence of a complete set of mutually orthogonal Latin squares of order n, or equivalently, the existence of a complete orthogonal array OA of n+1n is equivalent to the existence of a projective plane of order n, whose existence is known to be equivalent to the existence of an affine plane of order n. Let us generalize the notion of extremality. Let A be a complete orthogonal array of type OA of type n+1n, and let A1 be an orthogonal array OA-Mn obtained as a subset of rows of A. For such an orthogonal array A1, whose block graph has non-canonical cliques, we say that the block graph is A extremal if the block graphs of all orthogonal arrays of type OA m-1n obtained as subsets of rows of A have the strict-EKR property. In this sense, extremal Peisert-type graphs considered in this lecture are a G2Q extremal. So we, in this sense, we consider them with respect to the underlying affine plane G2Q. And the idea is that we can consider a different affine plane. This is the condition by Gotzel and Marr, a bound, a condition. Let us discuss it. If OA-Mn is an orthogonal array with the property that n is strictly greater than m-1 squared, then the only cliques of size n in the corresponding block graph are canonical cliques. Let m-1 be a prime power, then there exists an orthogonal array with parameters m, m-1, and using Mach-Nash construction, it is possible to construct an orthogonal array of type m, m-1 squared from this array. This larger orthogonal array has OA m, m-1 as a subarray, and thus the corresponding block graph of the resulting array, orthogonal array, has the graph DOA m, m-1 as an induced subgraph. Since this subgraph is isomorphic to the complete graph on m-1 squared vertices, this induced subgraph is a clique of size m-1 squared in the block graph of the bigger orthogonal array. And this clique is not canonical. Let us recall the definition of bare subplanes. Let pi be a finite projective respectively an affine plane of order n, and pi 0 a projective respectively an affine subplane of pi of order n0 different from pi. Then it is well known that n0 is less or equal to square root of n, and if n0 equals square root of n, then pi 0 is called a bare subplane of pi. Thus, bare subplanes are biggest possible proper subplanes of finite planes. Gotzel and Marr propose the following problem. Assume that OA m, m-1 squared is an orthogonal array, and its orthogonal array graph, that is the block graph, has non-canonical cliques of size m-1 squared. The question is, do these non-canonical cliques necessarily form subarrays that are isomorphic to orthogonal arrays with entries, say 1, so 1 m-1. So the question is, do these non-canonical cliques necessarily form subarrays? And since our family XQ, our family of extremal Peisert-type graphs in square case corresponds to this case of orthogonal arrays, we investigated this question whether these extremal Peisert-type graphs give a negative answer for the problem Gotzel and Marr, but we just realized the following. The non-canonical cliques in the extremal graph XQ correspond to orthogonal subarrays OA square root of Q plus 1 square root of Q, which are just bare subplanes in AG to Q. The main implication of this result is that the block graphs of orthogonal arrays obtained from the affine planes AG to Q do not give a negative answer for problem 3. The following problem naturally arises. Let A be an affine plane of order Q such that Q is the square of a prime power and A is not isomorphic to the affine plane AG to Q. Do the block graphs of the orthogonal arrays obtained from square root of Q plus 1 parallel classes of A have non-canonical cliques without a subarray, or equivalently without bare subplane structure? Since there are many different affine planes known, in the case when Q is a square, we plan to investigate this problem and look at block graphs of orthogonal arrays obtained from affine plane from parallel classes of affine planes different from AG to Q. In general, the following problem is of interest. Let A be an affine plane of order Q such that A is not isomorphic to an affine plane AG to Q. What are A extremal block graphs of orthogonal arrays? Note that problems 2 and 3 are special cases of the most general problem of determination all the maximum cliques in the block graphs of an orthogonal array. And let us give some concluding remarks to this final lecture. In this final lecture, we have discussed extremal Peisert-type graphs of type MQQ without strict EKR property, that is, Peisert-type graphs having non-canonical cliques and the smallest possible number of canonical cliques. In particular, we determined the value MQ and explicitly constructed an extremal graph for every prime power Q. And in case when Q is prime, a square, or a cube but not a square, we showed the uniqueness of the extremal graph. It is an interesting question whether the uniqueness result extends to any other values of Q. In a similar manner, given a prime power Q, there exists the largest value of M, say capital MQ, such that there exists a Peisert-type graph of type MQ with strict EKR property. One can also call such parameter capital MQ extremal, but for graphs that do have strict EKR property. A Peisert-type graph of type capital MQQ with strict EKR property is called extremal. And problem 4, given a prime power Q, determine the value of MQ and characterize extremal Peisert-type graphs that do have strict EKR property. And let us give, this is the last slide in this mini course. This is a conclusion to the mini course. In the frame of this mini course, we have formulated many conjectures and open problems. Personally, I'm very interested in all of them and going to work on them with my colleagues and students. If you have interest in any of them, please let me know. I would be very happy to have new collaborators and thus more chances that these problems will be solved. And to conclude, I express my deep gratitude to the organizers and all participants. Thank you for your attention.
Thank you,
Thank
Sergey.
you.
Thank you for the lecture. Yeah. Questions?
Yeah, about the extremal, the other extremal graphs.
Yeah.
Yeah, so can you go back to the tables?
Yeah, right. The parameter capital MQ can be seen from some of the tables already.
Yeah. So as far as small, for small q, those extremal graphs are unique. So with strict EKR graphs with largest
for q equals 7, it is not unique.
See, it's not unique. Okay. Yeah, that it also not unique for q equals 13.
Yes.
Okay.
But it's unique for q equals 17.
Mm-hmm.
And not unique for q equals 19. But the next two cases do not provide, the next two tables do not provide the information already.
Yeah. Okay, thank you. And you mentioned hyperbolic quadratic.
Yeah.
To construct an affine polar graph. There's also another kind of affine polar graph called parabolic quadratic. Yes. They don't. There is no connection to Peisert-type graph.
We didn't find no connection. For us, it was a surprise that the extremal graphs in square case are isomorphic to affine polar graphs. We could not expect it, and first we realized that the extremal graphs are rank 3 graphs, and then we tried to realize which kind of rank 3 graphs they are, and found by computation that they are isomorphic to affine polar graphs of hyperbolic type, and then we just explicitly established the isomorphism.
Okay. And then also, I think not this lemma 1, but I think you have another lemma 1 about equality in weight distribution bound.
Lemma 4.
Lemma 4. So not in item 1 and 2. Can you show me item 1, 2 instead of 3, 4?
Okay.
Yeah. Yeah. So this characterizes equality in weight distribution bound.
Yes, if there is an eigenfunction whose cardinality of support meets the weight distribution bound, then its support induces a subgraph of special form.
So this is for strong irregular graph. Is there an analog for distance regular graph?
Yes, actually, in this paper by Krotov, Mogilnych, and Potapov, it was originally formulated for the negative eigenvalue of a distance regular graph. And this lemma 4, this is just a special case of that general result. And since the negative and the positive eigenvalue of a stronger regular graph and its complement are connected, we can apply to the the bound holds for any eigenvalue of a distance regular graph in general. But this characterization in terms of induced bipartite subgraph not necessarily complete in the case of the smallest eigenvalue of a distance regular graph. So in case of the negative eigenvalue of a distance regular graph, if the weight distribution is tight for the negative eigenvalue of a distance regular graph, then there exists an induced bipartite distance regular graph with parameters derived from the parameters of the original stronger regular graph. And actually, in their paper, it is interesting that they proved the tightness of the weight distribution bound for the negative eigenvalue of all Grassmann graphs. They found an embedding of a dual polar graph into a Grassmann graph. A dual the corresponding dual polar graph is bipartite, and they show it that this gives an eigenfunction whose support meets the weight distribution bound. So it is it is thus known that the weight distribution bound is tight for the negative eigenvalue for any Grassmann graph.
I see. Yeah, but the bipartite. The bipartite dual polar graphs are the one from hyperbolic quadrate. Yeah, okay. Yeah, I will look investigate the Krotov's paper. Yeah, thank you very much.
It's very interesting, and please have a look at the survey by Valuzenich and Sotnikova on this problem. on the problem
Uh-huh.
of I mentioned this survey in one of the lectures. Maybe I can send you the link to this survey, because they discuss the problem of finding the minimum cardinality of support in detail. And they give some new insights of the weight distribution bound in their survey. So somehow the survey extends the original paper by Krotov, Maginik, and Potapov.
Okay, thank you very much.
Yes, thank you, Sergey. Thank you very much. Well, so this project is just at the beginning, right? Yeah. Well, of course, a lot of results were done by you, but still there are many open problems.
Yeah.
Yeah, that's right. Yeah. Okay, thank you. Thank you so much. Yeah. Yeah, it was really very nice to have these new results and to have some new feelings about some connections with the theory and strong irregular graphs and Peisert graphs. So yeah, it is interesting, very interesting. Thank you so much.
Thank you very much for this.
Yeah, the mini course is done, and yeah, it was the last lecture, but I hope, yeah, we will have a lot of some other lectures given by you somehow. I don't know.
Okay, thank you.
Yeah. Okay. Thank you. Okay. See you.
Thank you very much.
Thank you very much.
Somehow.
See you.
Yeah.
Bye. Bye.
Yeah. Bye.
All right.